From MIT's Office of Digital Learning, this is Climate Conversations by ClimateX. I'm your host, Rajesh Kasturirangan. Welcome to Climate Conversations. I'm Rajesh Kasturirangan, and I'm here in MIT's Office of Digital Learning with two of my colleagues, Dave Damloor.
Hey, so glad to be here.
And Laura Howells.
Hi, everyone. So, what have you been reading about, Rajesh?
Well, do you want the good news or the bad news?
Well, we're a climate change podcast, so let's go for the bad news.
Well, no shortage of that. So I was reading this paper, it was really an article in The Ecologist, where they're talking about what might happen in Bangladesh. And based on the current population estimates, which might increase a lot by the end of the century, 30 million people will lose their lands if sea level rise is a meter or higher, which is what we expect by the end of the century.
Wow.
So that's 30
At
million
least.
people. Yes, at least.
And are there adaptation plans in place or the finances to support any kind of adaptation?
So the article does interview people in Bangladesh who have been tasked with that particular problem.
God, I wouldn't want to be given that problem.
Exactly. But, 30 million people, I frankly think that it's hard to plan for that kind of stuff,
Yeah.
even in countries where you have plenty of resources.
It's hard to even conceptualize.
But, that's the kind of saddening news, because there are low-lying areas and islands and places that are vanishing under the ocean.
Well, today we're going to be talking with someone who's thinking about these kind of problems.
Yeah, we have Professor David McGee, who will be telling us both about the history of the climate and the work that he's doing with very talented students on how to address major climate challenges, including in Bangladesh. But I think that we all have to face these challenges and not just David McGee's students.
Yeah, absolutely.
So
Yeah.
if you have any thoughts on how to do it, please contact us.
Let's take a listen.
So we're so happy to have Professor David McGee, who is an associate professor in the Department of Earth and Planetary Sciences at MIT, where he researches paleoclimatology, a term that I have to say 3 times before I even can pronounce it. But we are so happy to have you, and he's also the director of the Terrascope program, which is a wonderful undergraduate learning experience here at MIT. David, and since there are multiple Davids here, we'll call David McGee David, and we'll call David Damloor as Dave. So, David, tell us how you became a paleoclimatologist, and what do you do?
Yeah, I sort of thought that it was all an accident, that I just ended up doing this. And then I started to go through boxes in my parents' house, clearing out old stuff, and realized that it's been a little bit more linear than I thought. So I found a story that I'd written in first grade about a time machine that took people back to the Archean 4 billion years ago. So something captured my imagination really early on about times that we can't directly observe, that we don't have any written record of when the Earth was dramatically different than it is today. And about the basic fact that the Earth we look around and see around us today is what it is, but it's different than the Earth was a few million years ago. It's different than the Earth will be in a few million years, that the Earth is in this constant state of evolution.
Wait, I thought that the Earth started 4,000 years ago.
Right. It's much better job security for me to have another billion years or a few billion years to look at.
Where does the clock start for you?
The whole of Earth history is interesting to look at, and there's a huge amount of climate history that we can learn from. My research focuses specifically on the last, say, 500,000 years of Earth history. And this is a time period where the Earth has been swinging in and out of ice ages about every 100,000 years, going back and forth between ice ages like the most recent one being about 20,000 years ago to warm periods like today. And the reason for focusing on that time period, one of the reasons is simply that there's a better record. It's more recent, and so there's just more materials to study, more sediments, more other deposits to study, like ice cores. And so we can get a richer picture of what the climate was like in this more recent part of Earth history. The other reason is that the tools I use are best suited for the last 500,000 years.
I have so many questions in response to that. Question number 1. Is this oscillation cycle of ice age and back to warming typical of the last, say, 500 million years, or is there something special in the last 500,000?
That's a great question. So one of the things we see really quickly looking at the rock record is that the paleoclimate record, that is the record of the long history of Earth's climate, is really well suited to teach us about times when Earth's climate was warmer than present. And that's because for most of the last 500 million years, 500 million years, the Earth has been warmer than present. It's had less ice, sea levels have been higher, temperatures have been higher, CO2 has been higher, and all for natural reasons. And over the last, say, 30 million years, the Earth has been cooling, not in a constant rate, but has gradually been cooling. More ice has been building up. And the last 3 million years, that cooling has continued. And on top of that cooling, the climate has gotten more variable. So these swings between ice ages and warm periods are a somewhat unusual part of Earth's climate history. And that makes it particularly fascinating to study.
So kind of a geek question alert here.
Yeah.
So is that a kind of damped oscillation?
Yeah, so we understand that these ice age cycles are triggered by periodic changes in Earth's orbit that change how much sunlight is reaching the high latitudes in summer. Because that's what matters to an ice sheet, is how much does it melt during the summer. And so because there's these slow changes in Earth's orbit that change basically how much sunlight is reaching northern Canada, Greenland during local summer, that causes ice sheets to naturally grow and decay. What we also understand is that these periodic changes in Earth's orbit that have timescales of between 20 and 100,000 years are not sufficient to produce the ice age cycles that we've seen, that they need what we call amplifiers, things to make them larger than they otherwise would be. And so what we now understand is that the carbon cycle, that is movements of carbon from the deep ocean into the atmosphere to cause atmospheric CO2 levels to rise and fall, are what provides the amplification that's necessary to move the Earth between these climate states. One thing that we don't really understand is why the climate states seem to be fairly stable. That is, we move between them, but most of the warm periods of the last million years have been roughly about the same temperature and CO2 level. Most of the cold periods of the last million years have been about the same amount of ice growth and about the same CO2 level. And so there's some suggestion that there are quasi sort of stable states that the climate is moving back and forth between.
So one of the things that I'm curious about is the globe, is the entire Earth your field of study? Or when you talk about ice ages or going back and forth between warm and cold periods, are those localized, or how do you study in terms of the globe versus some subpart of the globe?
So some properties of past climate are global, like CO2 levels in the atmosphere, or of course, mean global temperature by definition is global. And so during ice ages, yes, the whole Earth gets colder. What I focus on, though, is not so much the global picture, but how these past climate changes have affected precipitation patterns. And that, by focusing on precipitation, that inherently brings you down to regional scales.
Okay.
So, for example, asking, when we've had these past climate changes, how and why has precipitation changed in the American Southwest? And do we understand the magnitude of those changes? Or, for example, in North Africa, in the Sahara Desert, has the Sahara Desert been equally dry throughout the last few million years as these ice age cycles have come and gone and as other changes have happened in Earth's climate? Or have there been dramatic fluctuations in how dry the Sahara is, or how dry the tropics are, or wet the tropics are?
I'm interested to know, you're talking about some obviously very complex measurements, and you mentioned one of the reasons you really like studying the last 500,000 years is because of some of the tools you can use. I'd be really interested to know what those tools are, what they allow you to measure and study, and how.
Sure. So we look at several different archives of past climates. So these are all natural deposits that form, and as they form, they encode information about the climate around them. So one that's especially easy to understand might be a tree ring. As a tree ring grows, in a year in which the tree has enough water and temperatures that favor growth, that's going to be a fairly broad ring. The tree will be able to put on a lot of wood during that year. During a year when the tree is stressed, either because of drought or because of a cold summer, depending on where it's living, it will put on a thin ring. And so you can go back in time, and if you take samples from many, many different trees to kind of filter out the noise of individual trees' life histories, you can start to reconstruct dry periods and wet periods in places where trees are mostly stressed by drought, or warm periods and cold periods in places where trees are mostly stressed by summer temperatures.
So if you don't study trees, what is it you study, and how do you pick your field sites? Because obviously you want to get data that maybe will supplement your prior research.
That's right. So the easiest type of deposit to understand that we study is ancient lake shorelines. So in many areas of the world, for example, Nevada and Utah in the American West, lake basins are hydrologically closed. That is, there is no river outlet. The lake just fills up and loses water by evaporation. This makes them fairly simple systems. It's like filling a bathtub. And as rain falls, it fills up the basin, and then of course you lose that water by evaporation.
So it is kind of like tree rings, right? Because more water, bigger lake.
That's right. Yeah, that's right. And it produces rings. It produces
Exactly.
rings around the essentially bathtub rings around the sides of the basin. And so we are all throughout the American West around what are either now dry basins today or small lakes like the Great Salt Lake or Pyramid Lake or Mono Lake. There are bathtub rings providing records of much larger lakes in the past. So, for example, the Great Salt Lake is a remnant of a lake that used to be the size of modern-day Lake Michigan about 16,000 years ago. And
that's recent.
yeah, so not that, this is just before we think people started arriving in this area of the world. The first humans to come into Utah, if the current dating is correct, around 13,000 years ago, would have seen a much larger lake than we see today. So this evidence of these dramatically different precipitation patterns that these lakes provide gives us a natural experiment to explore. What is it in the climate system that can make the American West so wet? And do we understand what these mechanisms are that lead to dramatic changes in how wet or dry the American West is?
So what are your theories?
Yeah, exactly. That was my question.
So one of the big things that matters is these ice sheets that have occurred throughout the last 500,000 years. So just putting a really big ice sheet on Canada, as we had 20,000 years ago, diverts the same storms that today hit the Pacific Northwest and make it quite wet and pushes them further south, simply because of the topographic effect of a several kilometer high ice sheet. It's like putting a mountain range there. But there's other things that are important as well. And so one of the things that we're just starting to uncover is a relationship between essentially the relative heating between the two hemispheres. So when the northern hemisphere is slightly cooler relative to the southern hemisphere, this basically pushes all of those storm tracks even further south and leads to the wettest conditions that have been seen in the American West in the past, say, several 100,000 years.
So tell us a piece of evidence that you had not expected to be useful for your purposes. So, something that's not as obvious as bathtub rings or tree rings.
So, yeah, the lake shorelines are particularly obvious and easy to understand. And I should make clear that the particular thing that we do in my lab is to date those shorelines as precisely as we can using uranium and thorium isotopes. And by dating them very precisely, we can then link them to other deposits around the world that have also been precisely dated to start to produce maps of past precipitation patterns. So we're not just looking at one place in isolation, but we're putting that in the context of as many other places on the planet as we can. So we start to map out, well, where were the dry zones? Where were the wet zones? Where were winter storms going? Where were the deserts at different times in Earth history? And that depends upon accurate dating.
And is that now available for a lot of the Earth?
Yes, we're starting to build much richer data sets. One of the ways in which these maps are useful is that we can use them to see how the same climate models that are used to project what changes are expected in the future behave when you take them outside of their comfort zones. That is, all of these climate models are simplifications of the actual climate system, and they've been tuned or developed to reproduce the patterns and the variability of the 20th century, the only time period in Earth history where we have a good network of instrumental data, direct observations. And that's great. These are robust models, and they produce relatively consistent projections for the future. But going forward, we're starting to push the climate. We're already pushing the climate outside of the range of variability that has been observed in the 20th century. And so the question arises, do the same tunings and parameterizations, the simplifications that worked in the 20th century, will they work in the 21st? Will we get accurate projections of where we're going? And so one way to provide an independent test of climate model performance is to go back to the paleoclimate record. I want to make clear that none of these paleoclimates are analogies to where we're going. We don't view any of them as saying, okay, because this happened X thousand years ago, Y is going to happen in 2100. But what they do provide is a time when the climate system has been kicked by something different than the 20th century and moved to a different enough state that it's an independent test of whether the climate models can match what the paleoclimate evidence is. And so we will take the same climate models that are used to project the future, give them the conditions of some time slice in the past, say 6,000 years ago, and then run the climate models under those conditions and then compare them to these dense networks of paleo data to see whether they reproduce what the paleo data say.
It reminds me a lot of what machine learning people do, right? Because they will take a test data set, but then set aside some of that. So they will create a model on the basis of a subset. And of course, before you predict what might happen in the future, you want to see if your model does well on the remainder of the test data.
That's right. And the
Right.
problem with the climate data we have now is that a lot of variability in the climate system is on timescales of 50 and 100 years. And if you will only have 100 years of data, it's hard to know whether you're capturing that longer-term variability. So, for example, tree ring records from the American West would suggest that in climates not so different from today, there have been century-scale droughts that are bigger than anything that we've seen in the last century. And so we're still working to figure out what caused those droughts. But they're a reminder that we might not have seen, we certainly haven't seen all of the variability that exists in the climate system, and we haven't been able to directly observe it. And because we don't have written records of climate everywhere in the world before, say, 100 years ago, we need to go out and use these sometimes complicated but important natural archives to reconstruct what climate was like in the past. You asked something about other pieces of data and surprises. So some of the other archives that we work with are stalagmites from caves and deep sea sediments, and each records a different part of the climate system and also has its own blind spots and strengths. And so one of the things we try to do in my lab is develop climate records using many archives, compare them to data that other labs have produced with still other archives, and produce as rich a picture of past climates as we can. We don't take any of these lines of evidence as the be-all and end-all, because each is a natural system that's reacting to many different things. Even the lakes that I talked about before, of course, a lake size is dependent upon how much rain falls, but it's also dependent upon how much evaporation there is, how strong winds are, and whether there's ice covering the lake in the winter and other complications. And so what we look for is consistency between multiple lines of evidence. And when there's disagreement, then we need to burrow in and try to understand these natural systems better to reconstruct past climates.
So I'm trying to channel some of our listeners. We have quite a broad audience out there listening to this podcast. So I'm wondering, one of the questions that those folks might ask would be, okay, so Professor McGee, tell me how all this research could inform what we're doing, the problems that we're facing today, and the questions that we're asking ourselves. How on earth do we grapple with this climate change?
I think there's a specific answer to that and a more general answer. And the more general answer is that the paleoclimate record provides clear evidence that when the climate system is forced, when it's pushed by something, whether it's greenhouse gases or changes in the Earth's orbit, volcanism, it reacts, and that precipitation patterns have the ability to change rather dramatically compared to what we're used to. 6,000 years ago, the Sahara Desert didn't exist. It was basically a grassland with hippopotamuses and giraffes and people living there.
Hard to imagine, yeah.
And of course, the evidence of Lake Bonneville, this lake that filled the Great Salt Lake Basin to the size of Lake Michigan. So these changes are very recent in Earth history, and at CO2 levels that are not that different from the levels that existed in the pre-industrial climate. And they suggest that the climate system responds. It is not a stable system. So my concern going forward is that we have infrastructure and societies that are built around the climate of the last 100 years. Our bridges, our ports, our highways, our farming systems, our irrigation is built around what we've come to expect over the last 100 years. And there's nothing sacred or special about the particular climate in which we live, but we're used to it and we've built around it. And so as we move forward and change the climate, my real concern is that it's going to be a fundamental and profoundly far-reaching, destabilizing influence. And it's going to make it harder to achieve all the other goals that we'd like to achieve this century, preserving parts of the biosphere, bringing people out of poverty, et cetera, by destabilizing the natural systems that we've come to depend upon.
Have you found that there's been an increasing political interest in the research you do? How do you find it communicating what you study with the world at large and the politics at large?
The really heartening thing is how much interest there is. We go out with the lab and go out to the Cambridge Science Fair or go to school visits or, podcasts like this. And there's just real curiosity and kind of wonder. And I want to remind us all that there's a big element of wonder to all of this research, that it's just fascinating that the climate system has been as different as it has. And it's important to understand that. And to some extent, it's not a matter of your political persuasion. The Earth has just been different in the past, and it's important to understand
it's
that.
a scientific fact.
It's just a scientific fact. And but that said, this research does have implications that we do need to pay attention to going forward. Whenever our papers are picked up in the popular press, you can go into the comments section and read a lot of
it's a dangerous activity.
It is a dangerous activity, and I don't do it too much. But one of the common responses is, well, the Earth's climate has constantly been changing in the past. So why should we care?
I hear that all the time.
The Sahara Desert didn't exist 6,000 years ago. It wasn't because people were driving Hummers around. That was one of the comments on, I think, one of our pieces. Yes, as I said, there's nothing special about the Earth's climate today. It's been warmer in the past. It's been colder in the past. CO2 has been higher. It's been lower. But we depend upon the climate that we have right now, and that's what we're insured against. That's what we're building around, and so what we depend upon is stability. And if there's one thing that paleoclimate studies teach you is the instability of climate.
So you've been reaching out to students at the Cambridge Science Festival and other venues, but you're also running a wonderful experiment here at MIT itself, which is Terrascope. It's a residential program for MIT students, isn't it?
Freshmen in particular.
For freshmen. So can you tell us exactly what Terrascope is and what do students do to get in and what do they experience?
Sure. So Terrascope is what's known as a freshman learning community at MIT. It's something that freshmen freely choose to join if they're interested. It's a group of about 50 freshmen every year who, in addition to their normal core classes in math and physics and chemistry and biology and humanities, take an additional course in the fall and then take courses in the spring focused on tackling some of the biggest challenges facing society in the area of environment and sustainability. So each year we choose a topic. That might be about energy supplies, it might be about freshwater in the American West, it might be about sustainable agriculture, and give it to the freshmen and basically say, run with this. Come up with a plan to address this challenge, and at the end of the term, you're going to be presenting it to a panel of experts we convene from around the world. And the intent has a few different elements. One is to get freshmen from day one thinking about how what they're studying at MIT relates to these fundamental problems facing society. The second is to give them a freshman class that's profoundly student-centered. They own the plan that comes out, they own the product that comes out, but they also own the process of how they get there. None of them have been surrounded with the sort of talent that they are surrounded with from day one at MIT. And so sitting in a class of 50 students who are all MIT freshmen is daunting and challenging, and it's a really important experience for them to think about, okay, how do we get everyone working together? How do we break this seemingly intractable problem down into manageable pieces and make progress and communicate with each other between groups and within our groups as we move forward? And so we are there as instructors not to give them a recipe for here's how you make this beautiful product at the end, but to help them reflect along the way. So after a week, we might say, okay, stop. How's your group going? What has worked well? What hasn't? And along the way, they think they're solving the world's problems. Mostly what they're learning how to do is to work in teams on a really big, complex problem that incorporates science and engineering, but also incorporates economics and public policy and sociology. That's the fall term. And so they emerge from that kind of daunted by the complexity of this problem, but also empowered by the process of having come up with a plan that they've defended in front of experts. That's a really powerful experience.
What is this year's problem?
So this year's problem I'm really excited about is
we are too.
Is about the challenge of climate change adaptation. That is preparing coastal communities for the impacts of climate change. And we're asking the students this year to focus on two very different coastal communities. One is MIT itself and Cambridge. MIT and Cambridge are just starting to identify the vulnerabilities that they have to climate change over the coming decades. And these consist of heat waves, flooding from more intense storms, and then also flooding from storm surge and sea level rise. And so they're at the point, both MIT and Cambridge are at the point of having identified the vulnerabilities, but they haven't developed a plan yet. And so we now bring these reports to the students and say, okay, here's the problem. What are you going to do about it? And then the other community they'll be looking at is southern Bangladesh, a place that is presented with profound challenges from climate change and has very different resources to respond. So they'll be working with experts from both regions. I should also say that as
will they be traveling to Bangladesh?
So they will not be traveling to Bangladesh. They will be going. So every year we take a spring break trip to somewhere in the world that has to do with that year's problem, and that's designed to connect the students to the problem in the field, but it has a large function as a corrective action. Sometimes they emerge from the fall term thinking that a lot of the world's problems could be just solved by sitting in Cambridge and thinking deep thoughts and working with other MIT people. And then they go to this some place in the world that's actually dealing with the problem, and they realize, oh, there's a reason that things function the way they do today. And this is actually a lot more complicated than we thought. So it gives them sort of a dose of humility and reality, and that's important, I think. So this year we're going to the Netherlands, which has been described to us as Bangladesh with resources. So this is a place that has built up a lot of coastal defenses around the rivers and the ocean that threaten it with flooding, a place where they can see firsthand engineering projects designed around flooding, and then think about how those projects might have implications for Bangladesh and for MIT and Cambridge
So
as well.
I have kind of one of those double-blind testing questions,
Yeah.
right? So the students are going to spend a year making this plan for MIT.
Yep.
MIT itself is probably, through its faculty and other experts, doing the same thing. When they both table their report, who do you think is going to be better?
That's a great question. So I think the ideal would be that the final plan would incorporate elements of both processes. Certainly we will be inviting people from the Office of Sustainability, people from MIT facilities as experts and panelists at the final presentation to hear what the students have to say and to ask them tough questions about their plan.
And sorry, have there been plans in the past that have really surprised you, impressed you in a way that you just didn't quite expect from freshmen?
Every year they do something amazing. They are taking 4 of their classes and then this additional class, and somehow they come together, and it seems like nothing is happening and it's chaos for a long time. But then something happens in much the same way that it feels like to be in a theater production. It feels terrible for a long time, and then in the final week, it comes together. And I guess one example that seems to have been particularly successful is in 2012, they came up with a plan of how to address the world's need for strategic natural resources, things like rare earth elements and phosphorus over the coming century. And they produced a website that had their plan. And this website every month gets emails saying, okay, we've been looking at your website, what, blah, blah, blah. They think that Terrascope is this bunch of consultants who have, come up with this, amazing plan. It's really just freshmen who are saying, this is, just something we came up with. But it speaks to the quality of their work.
Or it speaks to the quality of consultants.
Right. So I should also say that in the spring term, and of interest maybe to the listeners of this podcast, to complement that kind of big scale planning process that's in the fall term, there are 2 other classes that they take. One is a design class where they're designing and fabricating specific technologies related to the year's challenges. So last year was on sustainable cities. So we had groups that were coming up with small-scale wind turbines for informal settlements, ways of incorporating plastic debris into adobe bricks, ways of putting more bikes on city buses so that bikes and buses could work better together. And so it gives them experience in design to address the problem of the year. And then of specific interest to the listeners of this podcast is a radio production class where they are tasked with trying to communicate about the year's problem to a broad audience. And usually this draws a lot of sound from the spring break trip and builds it into about a half an hour, 20-minute program that then gets broadcasted at MIT and then put out on the Public Radio Exchange and picked up around the country.
So terrific. I listened to the one from Mexico City last year. It was really creative and lots of fun to listen to.
That was a lot of fun. And the one from the year before that, from a trip to New Mexico that we took, that was really incredible. Look at sustainable agriculture, won the award for the best collegiate radio documentary of the year. It's a really nice piece. And so if people are interested in learning more about Terrascope, that's a great. You can go to our website, terrascope.mit.edu, and then you can navigate to the radio pieces, and they're a great way of learning about it.
So, David, every time when we interview someone, we end with what we call a magic wand question, which is, if you could wave a magic wand and make the world be better, at least the climate parts of the world, what magic wand would you wave, and in what way would you make the world better?
That's a really hard question. For a long time, I kind of diminished the importance of sea level rise. I thought it was kind of, not that important an issue. But as I've started reading up more and more about this year's topic for Terrascope, about climate change adaptation, particularly in places like southern Bangladesh, I get more and more concerned about sea level rise. And so if I could wave a magic wand and basically slow down these ice sheets from melting, and particularly slow down the kind of nonlinear loss of ice sheets, the really rapid responses of these outlet glaciers just funneling water into the ocean, or funneling ice into the ocean to melt. That's the first magic wand that comes to mind. But I only get one, is that right?
Yeah, that's it.
that's
That's the
it.
problem.
Oh, man.
That's why it's such a
Okay,
hard
well,
question.
hopefully other people choose different things, and so we can cover different parts.
No, we can just nudge the Earth a little bit further away from the sun, and it'll be fine.
Right. Yeah. Geoengineering. I mean, the neat thing about paleoclimate is that basically every geoengineering experiment is some sort
Has
of
been done.
has been done in the past. Somehow. Whether it's reflective particles from volcanoes or changing ocean chemistry or whatever, what have you.
All right. So we can learn from the past, and we can learn from the present, and we can learn from the future.
Yeah.
So thank you so much, David.
All right. Thank you.
Thank you.
Thanks.
Wasn't that the most interesting interview?
Yeah, it was fantastic.
Wow, very inspiring what those students are doing.
I'm actually quite jealous of what they're able to do and get involved in. It sounds so exciting. It's something I would love to have been a part of when I was in college.
I want to go measure some lake rings. I think that's what I want to do.
He made it sound so easy, didn't he?
Yes.
Well, the terrific thing for me was that they really cut the students a lot of slack and let them do a lot on their own. They provide resources and guidance, but they're not there heavy-handed, just telling them what to do and how to think about things. They're really helping them to be lifelong learners about this stuff.
I bet my daughter would like that.
For sure.
I think she feels like that there's some slack that remains. If you want to tell us what you've been up to this year, we would love to hear from you. So contact us.
Yep, you can get in touch with us either on the site where we're all members at climatex.mit.edu. You can send us an email, climatex_feedback@mit.edu, or you can get in touch with us on Facebook, Twitter. We're everywhere, whenever you want to find us.
And you can leave a comment just below this podcast.
Yeah, absolutely. Tell us what you'd like us to talk about next, any guests you'd like us to have on. We're all ears.
Thank you for listening to us, and goodbye from Cambridge.
Till the next time.
Bye.
You can find us wherever podcasts are cast, and we would deeply appreciate your comments on Apple Podcasts if you have the time and the desire to do so.